It's time for our first panel, and I'm very excited to welcome my good friend, Ed Niedermeyer. He's the Director of Communications at PAVE, and if you didn't remember, PAVE is the Partners for Automated Vehicle Education. Ed Niedermeyer is a great longtime automotive journalist, wrote a book recently called Ludicrous about our friends down at Tesla. Ed, are you there? And I'd love for you to introduce your panel and embark.
Hey, Charlie. Thanks so much for having me. Thank you for this warm welcome. As Charlie mentioned, my name is Ed Niedermeyer. I'm the Communications Director at Partners for Automated Vehicle Education. We're a coalition of now more than 80 companies in the driving automation technology space, as well as stakeholder nonprofits. Our mission is to educate the public about this technology in order to help facilitate sort of public conversation and help shape this the future of this technology, as Mark Roskin was saying, to help people imagine the future that we want to build together using this technology. Today we have a topic that has come up in our sort of development of curriculum around this technology. And as we sort of peel the layers off and try and explain sort of the core concepts of what's going on in autonomous vehicles, one of the things that really sort of leaps out as unique among many other technologies is sort of this tension between, on the one hand, the use of probabilistic inference, or what is commonly called artificial intelligence, AI, and machine learning. There's a lot of names for it. On the one hand, which many of us know from a wide variety of things. But then on the other hand, the really high level of safety required for any kind of autonomous vehicle. And the tension between these two is a really fascinating one. And today I'm really honored to be joined by folks from experts really from a number of PAVE member companies who are really just perfectly qualified to help us sort of tease apart the tension between these two aspects of this technology. So first off, I'd like to introduce from Velodyne, our host here today, Nandita Agarwal. She's the Senior Lidar Architect at Velodyne Lidar. Nandita, welcome.
Thank you. Hi, everyone.
We also have, hi, Nandita. We also have from Aurora, we have the Senior Director of Safety Engineering, Burhan Muzaffar. Burhan, welcome.
Hey, Ed. Thank you. How are you?
Doing well, thanks. Good to see you. And also from GADIC, we have Head of Systems, Kartik Tiwari. Kartik, welcome.
Hello, Ed. Thanks for inviting me.
Thanks for being here. And thanks to all our guests for taking the time to help us understand this really fascinating and important topic. So I want to start off, Nandita, with you. Autonomous driving systems are different from many other high-tech devices in that they have to perform to extremely high levels of accuracy and reliability in order for people to trust their lives to them. We talk about safety, we talk about trust. That's a really high level of reliable performance is really fundamental to building those things. Can you give us a sense of how stringent the sort of performance requirements are for these systems, so we can sort of frame this and understand what are we trying to achieve as we're developing these systems?
Right, absolutely. So just to give an idea about how stringent these requirements can be, we need to enable our systems, in our case, which is the autonomous vehicles, to detect something which is around 20 by 20 inches, like a cinder block, which is 150 meters away, with a resolution of 0.1 degrees for us to detect that, and with an accuracy of 3 centimeters, which is just 1/3 of size of a human finger, and that too within a couple of seconds. So we need to provide this accuracy with a very high degree of reliability. And not only that, we need to provide that under all the environmental conditions and covering all the possible corner cases. So this high level of accuracy with very high degree of reliability, along with the safety compliance, that industry defines, our auto industry defines, translates into our requirements. And this shapes our development processes. It starts literally from the design. It starts from the component level. We make sure we go through a thorough engineering validation test, not only at the system level, but at the component level. So this is how we have our PLC that attains safety and sustainability over time. We have absolutely no room to fail. We test, we learn, and we reiterate. And that's how we keep on feeding the learning process to our designs.
Yeah, absolutely. And then I want to also look at sort of the other side of this, which is, again, what referred to as artificial intelligence, machine learning, probabilistic inference. We all use these technologies in identifying people in our pictures, perhaps, or a number of other features, but trusting your life to this technology is a really major step for any technology, right? And Kartik, I was hoping you could help us understand, maybe put this in context of how big is the artificial intelligence challenge part of this, and can you maybe compare sort of, again, because AI is fundamental part of every autonomous driving system, but how does the challenge of that piece of this compare to things like maybe chess or Go, where AI has sort of demonstrated superhuman capabilities?
That's actually a really good question, because this is something that we at GATTEC actually do discuss a lot. This kind of teeters on a little bit of philosophical angle of what AI is capable of or what it's not. But the way we look at it is that a fully self-driving vehicle that can drive in any condition, on any road, anywhere in the world, has to have the same mental model as a human has, because that is what our safety threshold is at a minimum, which is a huge task. It's a enormously large data set of what we care about as people, what we care about as a civilization and a society, and how do we ensure that that an artificially intelligent system that we have, an agent that we have created, has the same overlap of the model of the world as we do. It cares about the same things as we do, and it doesn't care about the same things as we do as well. One of the things that Mark in the previous keynote mentioned was that the level of talked about a lot of comparison between aviation and our system and the autonomous system. It is actually there are a lot of similarities there, but the certain things that are actually way beyond the capabilities of what we can actually do in safety engineering for aviation have to be applied in autonomy. The examples of chess and Go are actually great, but we also have to understand that those are constrained environments. There are certain machine learning techniques like reinforcement learning that we can pretty easily just apply and then go to sleep and come back in the morning and see a superhuman chess player in front of us. That is unfortunately not something, and that should be applied. There is no beta testing for autonomy on public road. I know you'll get a chuckle, Ed, for this. There shouldn't be that. We at the end of the day, when we talk about safety, at the end of the day, what we are talking about is human trust in a system that they are going to interact with. Until we can have that trust, we shouldn't go over and start putting those vehicles out on the road.
Yeah, and Burhan, so you have, on the one hand, you have this really powerful artificial intelligence technology that really allows AVs to do all kinds of things that previously were impossible, but you have this huge challenge to get it to this level of reliability and verifiable reliability, right, that you require, while also operating in these incredibly complex environments and all kinds of conditions, as Nandita mentioned. How do we start to sort of philosophically reconcile all those different kinds of challenges? Where do you start with that?
Ed, you're sure there's a lot of challenges that we have to figure out, but at Aurora, what we have done is we've taken a holistic approach to safety, which is evident in our safety case framework that we have made public. The key is to follow a robust engineering design and development process. So for example, if you take a very complex problem and you look at it, at first it seems almost impossible to solve, But if you break it down into smaller chunks and you start seeing smaller problems with possible solutions, you then start solving them one at a time in a consistent manner. And then the problem doesn't appear that difficult. But unfortunately, with AVs, there's a lot of those challenges to be solved. So at Aurora, our approach is analogous to breaking down that very complex problem into smaller sizable chunks, which is what we have exactly done with our safety case framework. We have intentionally chosen to break that framework down into 5 smaller chunks, which you would see as our 5 major safety goals. These safety goals allow us to design a system while you keep nominal performance in mind. We have to be able to drive on public roads, keeping SOTIF type requirements in mind. You can't just drive slow relative to the other traffic speed or brake as often. That is unacceptable. That is not acceptably safe. Also, to ensure that our system is acceptably safe in presence of faults and failures, so we employ safe by design policies and techniques. And at the same time, while you are maintaining nominal functionality and fail-safe functionality, we do work as humans on a day-to-day basis. There's issues that come up. So we have the third principle that basically allows us to handle these safety issues in a corrective, preventative action manner, which you would kind of see in other safety critical domains like aerospace, rail, and others. And then fourth item, which is really our system is performant under misuse and unavoidable events. No matter what we do with limiting the ODs and other things, we have to design our system to be resilient, to be able to not be fooled by intentional misuse. And lastly, but very, very importantly, it is important that we function as a trustworthy organization. That is how we do work on a day-to-day basis. So if you look at all of these common best practices, they are very commonly practiced across all major safety critical domains. And we at Aurora have embraced this framework as how we do work on a day-to-day basis. In my experience from aerospace and high-speed rail safety critical domains, you would see these non-engineering but organizational items that are very critical how you do work on a day-to-day basis.
Yeah, absolutely. And Kartik, I want to go back to you really quick because Burhan just mentioned something that I think is really important, which is sort of breaking the problem into chunks, right? And you have that both in terms of the different parts of the system and being able to verify them, component levels as well as the system level, but then also, as you mentioned, the operational design domain, the ODD, limiting that. And I know that this is something that Gatik has thought a lot about. You're a middle mile trucking company. You picked that domain very specifically. Can you talk to us about the role that sort of limiting the domain plays in assuring safety with these systems?
Yeah, that actually is one of the key components in actually getting autonomous vehicles out on the road. This actually goes on a spectrum, on the same spectrum as the example that you mentioned previously of chess and go. Chess and go are the extreme example of limiting the constraints of an ODD, not for autonomous vehicles, but having it in a sandbox. We are obviously not working in a complete sandbox, but we have to draw a line somewhere, and this goes for everyone in the space, that we have to draw a line somewhere and figure out what exactly are the current capabilities that we can shoot for, and make it reliable. By making sure that we have known and constant bounds around what is expected of the system, so we can still follow the framework for safety, and making sure that we validate and verify and validate our system while actually bringing value to our end customer.
Yeah, and Nandita, even if you do limit your operational design domain, you still have within that domain all kinds of different conditions, right? And they could be physical conditions in terms of the kinds of traffic within it, but then weather. Weather, you can't put a wall around your domain and say only this kind of weather is allowed in, right? So talk to us about the role that perception plays in this piece of it.
Right. So perception is the key, right? And more quality data means better perception, and eventually it means it equates to better AI inferences, right? So when we talk about AI, since this panel is all about AI, let's think of AI as a box, right? Which takes a certain input and gives us a certain output. And here, output being the decision that we wanted to make under, again, as you said, different conditions, different environments. When we don't want to make that decision, we want AI to make that decision for us. Now, as I said, that takes a certain input. So now, based on the output is directly proportional to the input. So how great your input is will translate to how good your decisions are being made. And as you said, you want the AI to make those decisions irrespective of the weather conditions, be it extreme weather conditions or terrains, or for that matter, when you're going from a shaded zone to a sharp, bright zone, from a dry to the wettest weather to the winter time in Alaska to the hottest day in Death Valley, or maybe you're driving on an internal road and a parking lot or on a highway. You don't want your AI to be bothered. You want your data output, or in this case, the input to the AI box, to be the same irrespective of the conditions. So how do we make sure of that? How do we make sure that AI gets same input? By bringing redundancy, by bringing different sensors together. I don't think today we can say that it is only cameras or LiDARs that are enough. We need as many testing, sensing modalities as we can or available today to bring them together, make them robust, put them together, and make sure we are covered under all the conditions. So I think bringing all the sensors capabilities under one roof is one of the keys. Having better data and then having better perception would eventually, as I said, translate to AI inference, better AI inference, and that is where we can start putting our trust more and more on these autonomous vehicles.
Yeah, absolutely. And if you think about it, right, I mean, it makes sense when you think again about that board game analogy, right? If you're playing chess, there's no question about whether a rook is a rook or a pawn is a pawn, right? It just, you know it. But out in the real world, when you have these AI systems, you don't always necessarily know immediately what it is, and you need that super robust system.
And to that, I mean, yeah, as you were mentioning about the robust sensor suite and stuff, we do need to bring things together just to cover all those conditions. Like, cameras give us color to detect the spotlights, to detect the red light, and reading signs. And the radar augments our object detection, and then LiDAR gives you really faster and accurate measurements of distance and reflectivity that helps you in object detection and segmentation. So this covers whatever it brings, whatever the weather brings, whatever the terrain brings to you. You are more or less covered with all the sensing modalities put together.
Yeah, and Kartik, Nandita mentioned redundancy, but then there's also this concept, and she alluded to it, but of diversity of sensors, and we've seen, obviously there's sort of the big three that everyone is familiar with: the camera, the radar, the LiDAR, but we see sort of more and more sensors being at least experimented with, tested with. What is this diversity bringing to the table? Why isn't one sensor modality going to be good enough, or maybe even just two, maybe just LiDAR and camera or something?
Yeah, we actually look at the problem of AV with the end objective. Where at the end objective is safety. We can everyone can have different capabilities, give different feature set of the system, but at the end of the day, if you don't ensure that that particular feature set is safe enough to be deployed on the road, you cannot actually go in that direction. So to do that, all our discussions actually do rely on general safety frameworks of redundancy and of constraining the ODD, all the things that we have talked about. So in general, our first step is to figure out the bare minimum ODD that we can actually deploy our system, which also, by the way, does include weather conditions as well. Now, not all weather conditions are under our control. So there are fallback cases, minimum risk conditions, and all of that. But in the nominal use case, if an extreme weather condition is within the nominal use case, we do look at what are the during a particular failure of current sensing or a particular sensor, what exactly are the fallbacks, and are those fallbacks complementary to the existing perception system or the existing sensor. So all of these things do add up to the eventual goal, which is our safety benchmarks that we want to hit.
Yeah, and that brings us to a really important point. And Burhan, I'm hoping you'll help people understand this. But as you're working towards in development, ultimately you have that safety case. You need to be able to really demonstrate that you have verified to a very high level of confidence that your system will operate safely within the domain in which it's designed for. You mentioned Aurora Safety Case, which makes fascinating reading. And if this topic interests you, I think that's one of a bunch of resources that I definitely recommend giving a read to. But, would you help just sort of explain sort of that verification step and sort of how that frames this whole challenge that we've been discussing here?
I forgot to unmute the button. So, that's a good question. Like I previously mentioned, I've had the luxury of working in different safety critical industries like aerospace, designing rockets for humans, and high-speed trains that had to meet different safety requirements in the European continent from one country to another. So I have noticed there's a common theme, which is really just the way they do business. Is the safety is always at the forefront of everything they do. And refreshingly at Aurora, we put safety first in everything we do as well. And the way we do it is, like I mentioned a moment ago, which the safety case that we have made publicly available is in fact the blueprint of how we do our work in day-to-day basis, which includes engineering, non-engineering, hiring practices, pretty much everything every Auroran does on a daily basis. What we believe is creating a comprehensive and holistic approach to safety, which not only includes the engineering practices that I shared previously, but also things that are common across all safety critical domains, which is establishing safe by design engineering processes. Also promoting, and which is equally important, promoting and supporting a healthy safety culture, making sure that all engineering and non-engineering teams across the board can raise a voice, report a safety concern without any repercussions. And that's what we practice on day-to-day basis at Aurora. And above all, defining an industry-leading safety case framework, which I believe Aurora has taken a lead on this for trucks and ride-hailing platforms altogether. So that framework allows us to not only do work on day-to-day basis, but it also helps us to plan and scale our product for near-term deliverables and strategize what we need to do to bring safety to everybody in our society. It is because of this holistic approach, we're able to build a Aurora driver that can be deployed, which is our mission statement, safely, quickly, and broadly.
Absolutely. And I want to dive into that safety culture piece a little bit more in just a moment. But Kartik, actually, if we could turn back to you for just a moment, when you're pursuing this kind of really verifiable safety case, really demonstrating safety, and you have these sort of probabilistic elements within a system like that, sort of, can you help us understand a little bit sort of how you either sort of is it that you try and limit the probabilistic aspects? Do you simply get those aspects so they're performing and you can demonstrate that they're reaching a certain level of performance? Just kind of help reconcile those two concepts in that safety case framework for us, if you can.
Yeah, that's also a really relevant question in the industry, because at the end of the day, yes, we are building a cutting edge technology system and all of that, but we are also trying to end up going to use this in a business case. We want to build a business out of it, so we want to make sure that there is a product market fit somewhere here. That we can sell the existing capabilities to either as a product or as a service to a customer, and they can derive value out of it. So the interesting question then becomes is like what exact capabilities can we actually build in the system that we can that the customer can derive value of, and most importantly, they can be shipped in a safe manner to the customer. Those are the two really important questions, and the balance there. Then to find the balance there, we then have to dive into how much probabilistic system the system needs to be versus how much deterministic it needs to be. The reason why those two parts of the system essentially inform our decision is because the more probabilistic our components or our system is, the more statistical validation processes we have to use. I do use this example internally that we do have a lot of safety engineering best practices from aviation, from from incumbent industries, but they're pretty much deterministic. You have certain materials, you have a mechanical design. You can pretty easily see that 1 + 1 = 2 here. You can do a lot of those things. But the baseline of those things are also probabilistic. The time it takes for, let's say, a hinge to fail, you have to get it through an endurance cycle, which is a probabilistic validation technique. The same thing has to be done for machine learning. So the way that we focus on the problem is by dividing and conquering this complex problem, and figuring out where exactly are those probabilistic solutions and techniques most relevant, and then only apply it there while making sure that the rest of the system stays deterministic. So we are in this, we find the balance like that.
Thank you. Yeah, no, that's really helpful to sort of understand. And I know I really appreciate you all of your candor, because I know some of this stuff is hard to talk about in detail sometimes. But Nandita, as we sort of move towards the close here, I want to go back to what Burhan was mentioning about safety culture, because I do think that, oftentimes in the technology space, there is a lot of sort of bravado and around risk taking and entrepreneurialism and things like that sometimes do find their way into this space and frankly have in the past not always led to safe outcomes. And yet, I know from my work at PAVE that all of the companies represented here, and of course Velodyne, which puts on a World Safety Summit every year, the safety really is core to what you do. Why is it that the safety culture of this is so important in ways that maybe, for mobile apps or other kinds of technology that people think about it's just not the same?
Right. So unfortunately, safety cannot be an afterthought. We work for safety, we design for safety. So assessing safety is the most critical part of our product lifecycle here at Velodyne. Most of the safety requirements are helped defined by our friends like auto industry and by our customers. It actually really has to start from design, as Burhan was mentioning. Validation at a component at a subcomponent level is really important. We start with our DFMEAs, which is design failure mode effects analysis and process failure mode effect analysis. And we not only do that once we have some sort of subsystem assembly available or built, we go through a lot of validation tests. We have our own reliability labs where we emulate the shock and vibe, extreme weather conditions. So we take our sensor through an awful lot. We test them, we learn from that test, and we reiterate. We reiterate in those designs, and the process keeps on happening. And as we have discussed in this panel a few minutes ago, everything has to be with the baby steps. We learn as we walk along. It's kind of a journey that we're on together. So we do our reliability labs and our validation testing, our end of line testing is so thorough. This is where we make sure that since we are working for safety, we do not have room for failure, that we actually do not fail under any condition.
Absolutely. And as you've all mentioned, lives are really at stake in this technology, and that really is the heart of it. And as Mark Roskin so eloquently discussed earlier, the whole goal for this technology really is, or one of many goals, but really the central one in a lot of ways, is to just make our roads safer than they are today. Thank you so much to all the guests for taking the time to, first of all, for being paid members and for supporting our mission of helping educate the public, but also, giving of your time to help us explain and tease out these topics. I always learn from you all, and I really hope that everyone else has learned from this conversation as well. So Nandita Agarwal from our host here, Velodyne, thank you so much. Kartik Tiwari from Gadik and Burhan Muzaffar from Aurora. Thank you all so much